Hey everyone, I see it's right around noon here, Eastern time, so we'll go ahead and get started. Good afternoon, everyone, and thanks for joining us today for our CINA Distinguished Speaker Series session. My name is Carrie Riddle. I'm the Deputy Director with the Criminal Investigations and Network Analysis, or CINA Center. We're a DHS Center of Excellence here at George Mason University. As we get started, just a quick reminder to please keep your microphones muted. And following today's talk, we'll have some Q&A moderated by CINA's director, Dr. Jim Jones. So please feel free to type your questions in the chat at any point throughout the session today. And for our folks who may be watching through YouTube, if you have any questions along the way, feel free to shoot us an email. The address for that is cina@gmu.edu. If you're interested in checking out other CINA Center events, please check out the CINA website, cina.gmu.edu. There you'll also find a digital archive with videos of our speaker series talks, as well as information on CINA's research, publications, and other work in this space. And this afternoon, I'm pleased to welcome and introduce our speaker, Mr. Joe Weiss. Joe is an expert on control system cybersecurity with a broad range of accomplishments as both an industry professional and an author. In 2000, he helped start the Control System Cybersecurity Program for the electric utilities. Joe has also published over 80 papers on instrumentation and control systems cybersecurity, book chapters on cybersecurity for utilities, data centers, and cyber policy. And he has also authored a book called Protecting Industrial Control Systems from Electronic Threats. Joe has amassed a database of more than 17 million control system incidents. And he's an International Society of Automation Fellow, Managing Director of ISA 99, a Ponemon Institute Fellow, and an IEEE Senior Member. He also has patents on instrumentation, control systems, and operational technology networks. And he is a registered professional engineer with both CISM and C-RISC certifications. The title of Joe's talk today is called Control System Cybersecurity is More Than Network Cybersecurity. Joe, welcome to the CINA Speaker Series, and if you're ready, the floor is yours.
Thank you. Can you hear me?
Yep, I can hear you okay.
Fantastic. Thank you, and thank everybody for coming. And let me make sure that you can see the slides. Let's see, hold on a minute. Okay, can you see the slides?
Not yet, Joe. I'm not seeing them. Is anyone on my team seeing them? Are you sharing your screen?
I'm sure. Let's see. Let me check. Hold on. No. Let me do the share screen. And can you as a control system engineer, I'm used to things happening in real time, not within the day. So bear with me. Is it, tell me when you can see it.
Yeah, we're seeing your screen. We're seeing the thumbnails of the slides. So it looks like it needs to go in the presentation mode.
Yeah, that's what I'm trying to get to. So bear with me. While it's getting there, wanted to give just a little bit of background. Like I say, I am actually a nuclear engineer. And my first almost 20 years, I'm old, was, oh, there it is. Can you see it now?
We're still seeing the thumbnails of the slides.
All right, hold on a minute. Let's see, slideshow.
So I would try to go to the bottom footer bar to the far right icon.
All right, hold on. Apologies. At one point in time, we actually had this nailed down. Okay. Well, while this is getting there, let me kind of at least give a little bit of background, and I apologize for why this is not where, can you see this? If I have to, I'll just run it through this way, I guess.
Yep, if you also go down to the bottom right, there's a icon, yep, right
Yep.
there.
That's what I just hit. Let's see if that works. Bear with me a minute. Does this work now?
Perfect.
Perfect. Looks great.
Okay. So let's start. So to begin with, I use this front little thing, that little icon, or that little picture, if you see in the bottom, kind of explains a little bit why we have the problems we have. And that's that the networking world and the engineering world are square pegs and round holes, and look at life very, very differently. Like I say, I'm a control system engineer. All this says is I've been around a long time. But what I want to do is explain the title of my book. It's called Protecting Industrial Control Systems from Electronic Threats. And the reason for the title is hacking control systems is not difficult. Excuse me, protecting them is rocket science, because control systems have to work. And if you try to do so much that you, quote unquote, overly protect them, the control systems won't work. And you will have essentially accomplished what the hackers are trying to do. So the point being, what we're really trying to figure out is the balance between the systems working and the systems being protected. It says industrial control systems, and I wished I never used the word industrial. But the point is, this is all control systems, whether it's the term SCADA, supervisory control and data acquisition, distributed control system, programmable logic controllers, field instrumentation, chemical analyzers. For that matter, a control system is literally a ventilator. It could be anything that monitors or controls a physical process. And it says from electronic threats. And I'm going to go through this more, but the point being that I ended up changing the title from where I was originally going to do. This is like about 10 years ago, because I had started the first control system cybersecurity conference anywhere back in 2002. And when I had my first conference, I had 3 entities show up I didn't invite. Not that I didn't want them. It's just I didn't know who they were. The first was the National Transportation Safety Board. Now think about, why would NTSB be at a control system cyber conference? And the reason was they were finalizing the report of the Bellingham, Washington Olympic pipeline rupture that was cyber. The second was there was a country from Asia, or a couple of representatives from a country in Asia. I'm not going to mention who. I didn't know about them. They found out about me. And the reason they came is they had had a number of control system cyber incidents. One took out roughly 10% of the generation in their country. And the third was a friend of mine who I met, I didn't know at the time, who was from the Idaho National Laboratory. And that meeting at the conference led to me supporting Idaho in starting the SCADA testbed at Idaho. Well, fast forward the second conference, we didn't have a testbed yet. So I had a number of organizations give presentations on why they should be the testbed. Well, one of them was Navy Mission Assurance in Dahlgren, Virginia, not all that far from George Mason. And this is it. Everything I'm speaking about is unclassified, open. I have no clearances. So therefore, whatever you see is in the public record somewhere. But anyways, they gave two slides on Navy letterhead. The first one was a Navy destroyer was entering the port of San Diego, and they hadn't turned off their high power pulse radar systems. That Navy destroyer took out San Diego Gas and Electric and the San Diego Water Authority SCADA systems. And the second one, the Navy was doing some testing in Europe and blew up a 36-inch pipeline. So the point being, it doesn't have to be a 12-year-old pimply-faced hacker sitting at his keyboard trying to hack Windows. And I'll mention more about that as I go. And I wanted to also talk a little bit about history. PDD 63, Presidential Decision Directive 63, was signed in May 1998. This is what was supposed to lead to all of the critical infrastructures being cyber and physically secure. And you look what it says, no later than the year 2000, the US shall have achieved an initial operating capability, and no later than 5 years from today, the US shall have achieved and shall maintain the ability to protect the nation's critical infrastructures. That's 20 years ago, and we're still not close to being there. And that also says this is how many different presidential administrations. There's absolutely nothing political about what we're talking about. Also wanted to mention, where did the term cyber actually come from? The term cybernetics is the science of communication and control theory, for automatic control systems. Of all things, cyber actually started with the control systems engineers. It was totally interdisciplinary. Only over time, the term cybernetics got morphed into what you look at today as this term being cyber. And I think people may have heard of this term, IT-OT convergence. There may be a convergence of networks, but there's absolutely positively no convergence of functions. What the control system world does is completely and totally different than what the IT world does. Now, again, a couple of definitions that are really critical. The first, like I say, is that the definition of a cyber incident. To IT, the de facto definition of a cyber incident is you're connected to the internet, you're running Windows, and data is being maliciously manipulated or stolen. It's all about privacy, and it assumes that it is malicious. Because NIST has whole bunches of definitions dealing with cyber, and GAO put out a definition, as did ISA. ISA, for those who don't know, is the International Society of Automation, on the definition of a cyber incident. In fact, I am writing as we speak, excuse me, I'm sorry, what's called a micro-learning module to define what is a control system cyber incident. And for what it's worth, there are other organizations, one being the SAE, Society of Automotive Engineers, that is looking also to work with me on this. And I'll be going through a lot more detail on what these cyber incidents really are. But the point being, what it really is electronic communication between systems or systems and people that affect confidentiality, integrity, or availability. And the key point here is it does not need to be malicious. And part of it is, even if it was malicious, it is not clear we would know it's cyber. We don't have that kind of, if you will, technology. People have heard the term OT. OT, operational technology, was a term coined by Gartner because Gartner didn't know what a control system was. So they basically said, if you're not OT, or you're not IT, you're OT. Well, OT is not everything. Pumps, valves, turbines, transformers, the actual mechanical equipment is not part of OT. In a funny sense, what OT is really the networks that the control system world uses. It is not the equipment. Excuse me. And many of the people, the engineers themselves, do not consider themselves to be OT. They consider themselves to be engineers. So I'm also wanted to show, you see that little caption on the side. Sarah, is that visible to everybody? Anyways, the point being, that is the Purdue reference model. That is not the OSI 7-layer stack. And what the Purdue reference model does is basically shows where, if you will, in the hierarchy, and it's really based on timing, where the different systems are. So level 0 are things that happen in real time. That's your sensors and actuators. Level 1 occurs in, say, milliseconds to a minute or so. Level 2 is normally minutes. Level 3 can be hours. You know, you get to what's called the demilitarized zone. That's what separates the control system networks from the IT networks. That's where you start, you know, having long-term databases on the order of weeks, months, or years. There is cyber technology from essentially level 1 is iffy, but from certainly level 2 and 3, because that's more conventional networking type things. There is almost no cyber technology when you're down at the level 0-1 layer. Oops. Let's see where. Next slide. Oops. I'm sorry if I've lost the slides. Apologies. Let me see where we are. Here we are. Okay, this is my slide. That's really my techie slide, if you will. On the right, where it says IT, that's where you have your databases. It's where you have your connections to the internet, etc. And cybersecurity exists there, and it's pretty much native, if you will, internet network protocol type things. What you see in that inset is what looks like a little control room. And prior to Stuxnet, that's as far as cybersecurity went. And OT is really in that particular range. And what you have there are control system protocols that are in, if you will, IP wrappers. So most of those protocols have no security at all, but they're wrapped in IP, and that's where security comes in. Following Stuxnet, which if people aren't aware, Stuxnet was the cyber attack against the centrifuges in the Iranian centrifuge facility. And what they really, in a sense, were going after was taking control of the programmable logic controllers, because it was very minimal cybersecurity at that point in time. Well, today there is at least more. I didn't say total, but there's more cybersecurity when you're for the programmable logic controllers. But when you start looking at the far left, the pumps, the valves, the motors, the sensors, there is no cybersecurity in them at all today in any industry. There is no authentication. There is no attribution. There is no encryption. And yet, these devices have connections directly to the internet. One other thing I wanted to point out in this slide is you'll notice on the bottom looks like a cell phone, which is what it is. Today, there is software that sits on a cell phone or can be ported to a cell phone that essentially makes it a portable control room. From your cell phone, you can control an entire facility. From your cell phone, again, assuming you've got the appropriate software, you can get direct access to the sensors, to the motors, to the valves, everything. So you start thinking, not only is that a cyber issue, that also starts to become a very critical physical security issue. This is something that I think most people aren't aware of. I think a lot of people feel that this is all very proprietary information that nobody knows anything about. Russia, China, and Iran use the same control system vendors we do. Iran being a little bit different in that our US vendors can't support Iran, but those control system vendors that are not based in the US can and do support them. The only ones that people really aren't supporting, at least from the West, as best as I know, is North Korea. But Russia, China, and Iran have the same vendors with the same equipment, with the same training, and even more, the same default passwords as used in the equipment used in the US, Canada, Europe, Japan, etc. The US buys equipment and chips from China, as well as China buys equipment and chips from the US. The control system standards development, including cyber, have participation from all over the world. I happen, as a nuclear engineer, I'm one of the quote unquote designated US experts on nuclear plant cybersecurity. I'm part of what's called IEC TC 45. Several years ago, they had their meetings on nuclear plant cybersecurity in Moscow. The following year was in Beijing. The point that, again, the engineering disciplines, electrical, mechanical, chemical, nuclear, you name it, these disciplines are taught all over the world. So when people start thinking, well, nobody else knows this or nobody else will know this, that's wrong. People in all of these other countries know as much as we do. They have to in order to be able to run their systems. Now, as a university, this is very important because this slide shows, and I hate to phrase it this way, but that the universities are really the starting point for the problem we have to this day on, quote unquote, this culture gap between the IT or networking world, whether it's IT or OT, and engineering. Cybersecurity is taught within computer science. Very few universities anywhere in the world require anybody taking cybersecurity to have to take introduction to engineering. The flip side is all of the domain engineering disciplines, electrical, mechanical, nuclear, chemical, you name it. Very few universities have any requirement that they take an introductory course in cybersecurity. Think of, because you're a cybercrime center, think of the universities that teach criminal justice. And how different what I'm talking about is to anything you would be teaching in a criminal justice curriculum. What you have in that red circle is really a dot. That's the control system security experts, not OT security experts, control system. There are very, very few of those. We desperately need to get more. The reason you see the 4 arrows is so many more people are coming through computer science than the single arrow coming from the control system world. And one of the things that I wanted to get across is what you see at the bottom is, just because part of the system is not vulnerable to the threats you're used to seeing does not mean the system is not vulnerable. It just means it's not vulnerable to what you're looking for. And in a sense, this is what, Stuxnet, but it's also what Russia did with Triton and what China is doing with some of this, what they're doing with some of the equipment that's being sent to the United States and elsewhere. We need to be looking at everything, not just the parts that, we know or understand. This is just a little chart showing the difference, not between OT and IT, but between the networking world and the engineering world. And what you'll notice is almost every one of these major criteria, and I hope it's clear, confidentiality, exactly opposite. To the engineering world, it's trivial. Message integrity, really high. Availability, really high. Authentication, high, but it's simply not available. Our scope is more than just IP networks. We really don't have any cyber logging or forensics, nor cyber training for the engineers. Our equipment is there for, I say, 10 to 25 years. You may have equipment out there. The equipment itself could easily be 40 to 50 years old. A lot of the equipment we have, I shouldn't say a lot, certainly some, isn't just Windows, Windows 7 or NT. We still have equipment in critical applications with Windows 95. And it can't be replaced because the equipment was designed for that particular software. IT or networking is worried about data manipulation. We're worried about equipment damage and deaths. And even the standards are different. In the IT world, it's all about ISO 27000. In the engineering world, it's ISA IEC 62443. Now, this slide is meant to show that it's real. I mentioned there are more than 17 million control system cyber incidents today. What you're looking at on top is a data center, top left. In this case, at least one of the cases, they basically use the uninterruptible power supplies to fry every server in the data center. They didn't go after the data, they went after the hardware. What you see next to it is total destruction of a turbine. As best as we can tell, that we think was an actual attack. You're George Mason. The one on the right, you probably know about. That's the DC Metro Red Line train crash. That was control system cyber. I was actually put on a national transportation board to look at cybersecurity for mass transit. And for what it's worth, everything that occurred with that is not covered by what TSA now has with their rail cybersecurity requirements, because that wasn't networks, that was control systems. Bottom, sort of the middle, what you're seeing is that's the PG&E, Pacific Gas and Electric, San Bruno natural gas pipeline rupture. PG&E is a corporation. is now a convicted felon because of that control system cyber incident. What you see in the middle is the Bellingham, Washington Olympic pipeline rupture. 3 people were killed, 3 people went to jail. This directly led to the bankruptcy of the Olympic Pipeline Company, which was a joint venture of Shell and Texaco. And by the way, from a control system cyber perspective, Bellingham and San Bruno were almost the same, and yet neither of those are addressed by the TSA pipeline cybersecurity requirements. What you're looking at next to it was the Australian, the Marucci wastewater cyber attack. The disgruntled system integrator that caused it was caught the 46th time he did it on a traffic stop. And again, by the way, those kind of issues are not covered by EPA's cybersecurity requirements that were just issued. What you see in the bottom left, that was hacking the buoyancy system of an offshore oil platform to tilt it, to shut it down. And that's real. That really happened. What you see next to it is a 6,200 megawatt hydro facility in Russia. This lifted a 1,000-ton turbine off its pedestal, killed 75, and Russia thought we did it. What you see on that ship, brand new Navy ship, again, everything here is unclassified. Control system cyber damaged the propulsion system and had to be towed the final 40 miles into port. What you see on the very bottom right is something you never think about. This is a roadway. How can control system cyber affect a roadway? Well, in this case, this is I-70 in Denver, where they basically dug it out and put it underground. And it turns out that control system cyber occurred because the pumps to pump the water out of that submerged roadway system didn't work. And what you see is they had to literally rescue people out of their cars. The last one is the East Palestine train crash. One of the things that it showed was in, I believe it was in Salem. I think it was Salem. Anyways, 20 miles away from East Palestine. They were showing pictures of the rail car that actually had the burning wheels. The entire undercarriage was on fire 20 miles before East Palestine. And the monitoring systems didn't detect that as being a problem. What you see here is what I'm writing now, like I say, for ISA and what SAE wants to be involved with, etc., is what is a control system cyber incident? There's no definition. And in fact, what's happening is there are different industries that come up with their own definition in order not to have any be declared cyber incidents. And one of those industries that's doing that is the electric industry. There is no training to identify a control system cyber incident. There are no cyber forensics. And I'm actually working on a project. We just finished phase 1, and it's going in for phase 2 for an SBIR. Hopefully we'll get the award. I hope it's going in. But when an attacker is actually in your network, there is no technology to be able to mathematically determine where the attacker is going to go next. All of the technology is basically to say, did they get in and where are they now? So what we wanted to talk about because of this are both false negatives and false positives. Most people have heard of the Old Smart Florida water treatment cyber hack. This was back in 21. It turns out it wasn't a cyber attack. It was user error. Ironically, this event, which wasn't even a cyber attack, was the impetus for EPA to put out their water cybersecurity requirements. And they're really aimed at, in a sense, what happened with Oldsmar. I had put out a blog. In fact, I'd been asked by the staffers from the Senate Energy Committee to put the blog I had written into the Senate hearing minutes, which I've subsequently did. Well, in doing that, when I had put the blog out, a colleague who's actually in Canada had put out a survey last year to 200 Canadian executives, and they basically asked, have you had any actual, quote unquote, ICS or OT cyber incidents? And if so, what happened? Well, they got the normal, like I say, in addition to the usual suspects, loss of information, operational downtime, et cetera, we got these results. 14% said they had damage to equipment, 10% environmental damage. And then look at the next two. 7% said they had had injuries or death of employees from control system cyber incidents in 2022. 6% said injury or deaths to the general public. Now, the next two is why I wrote the blog and why this whole issue of identifying cyber incidents is so important. DOE has a mandatory reporting requirement called the OE 417s. It's for anything that could affect the reliability of the grid. And in 2022, DOE OE 417s, which is the utilities data, identified 10 cyber attacks that affected the grid and 35 complete loss of view and control in the main control rooms for more than 30 minutes. That's cyber, no two ways around it. NERC, the North American Electric Reliability Corporation, that's who they have the quote unquote critical infrastructure protection standards, the SIPs, the NERC SIPs, that is the cybersecurity requirements for the electric industry. They made quote unquote the same reporting, though it's not exactly the same, but they said no cyber incidents, no impacts on SCADA or EMS, despite the fact that 35 lost all view and control for more than 30 minutes. And here was the other thing that's actually in the report to FERC, to the Federal Energy Regulatory Commission. They had identified a physical cyber attack against a substation. And as part of that physical cyber attack, they used remote access to try and open the gate, the security gate. And they did not consider that to be a cyber attack. This is why it is so critical to be able to have a fundamental understanding of what is a control system cyber incident. The utility industry is trying to establish this new center, and that's going to be in conjunction with the intelligence community. Well, what good is it if you can't even get the information? Now, for cybercrime, normally you don't think of control system cyber incidents affecting cybercrime. Well, what I call Dieselgate, what Stuxnet was monitoring process conditions. This is, with the centrifuges, monitoring the process conditions. When it got to a particular process condition, they basically started the attack to damage the centrifuges. And when they were done, they put the control system logic back to normal so nobody would know anything happened. That is exactly what happened with the cars. Over 17 million of them. Now, another case, and again, there's a few, but here's another case. This was a labor action where what they ended up doing is going to the programmable logic controllers and changing the passwords. What that did is it locked out these control systems and effectively shut down that facility. So normally we think of control systems as being nation state or quote unquote disgruntled employees. But in certain instances, this can also very much be cybercrime. And I've got a slide a little bit later on dealing with ransomware and indirectly affecting control systems. The recent national cyber strategy was aimed almost exclusively at internet protocol networks. Well, control systems start out as analog and serial. None of that is being addressed in either the national cyber strategy or any of the guidance coming out. The cultural issues between engineering and network security were essentially exacerbated because here you have the national cyber strategy and the engineering world wasn't even mentioned. Real incidents continue to occur, but they're not being identified. And finally, you have the Cyber Safety Review Board. Well, that bothers me a lot with the term safety. There is nothing about the Cyber Safety Review Board that deals anything about the safety of people or equipment. We really need to make sure we're using the right terms. There is no representation from anybody on control systems there, which is the only thing where you would really see the word safety. Now, what this has also led to is, for those that are old or those that read history, during World War II, you had the Maginot Wall in France, and I guess down to Belgium. They built this big wall to keep the Germans out. And what did the Germans do? They simply went around it. Well, that is exactly what is happening now in the world of cybersecurity. The Maginot Wall is for the IP networks. What you see there is a picture of a transformer. What have the Chinese done? They've simply gone around it. And I just wanted to stick this one slide in. This is coming from, again, this is all public. The DNI had a national intelligence estimate, and what did they say? China is the world's leading supplier of advanced grid components, which we assess creates cyber vulnerable risks. This is transformers, circuit breakers, inverters. Inverters, that is all of your photovoltaics. That is all of solar. What you see there too, the U.S. has imported up, this is since 2022, since 2022, over 170 million inverters from China. What's in them? We also have had instances where we've had counterfeit process sensors coming from China. That's not just a cyber issue, that is a big safety issue. Now, I wanted to talk about process sensors. And in fact, I have to talk to, later this afternoon, the Secretary of Commerce's IoT Advisory Board on this whole issue of process sensors, because this is not IoT. What you see there is a rack of sensors. This is what measures pressure, level, flow, temperature, chemical composition, you name it. These are your eyes, ears, nose, toes. This is what measures things and sends them to the control system, or if you will, to the brain. There are no passwords. There's no capability for passwords. It can't take an antivirus. There is no authentication. You don't know if that signal is coming from the sensor or Beijing. There are, key management doesn't exist. These don't use Windows. There's no, when you think about patching, they use insecure sensor networks. The most popular sensor network for these types of devices in the world, there's, I think, more than 60 to 80 million of those devices are built on 1200 baud modem technology using what's called frequency shift keying, which is 1970s Bell technology, Bell telephone technology. This is the most popular sensor network in the world to this day, and more products are continuously being sold. They are 100% trust. They're not zero trust. They're 100% trust. CVEs, where you are looking at, vulnerabilities. CVEs don't apply because the CVE process is looking for security technology that has problems. These have no security technology. The whole concept of disclosure doesn't really work here. How large is the scope of these devices? I actually did a walk down of a 150 megawatt solar facility, roughly the same size as a small coal-fired power plant. There were 2 million panels there, each one with a sensor and inverter. A ship has 50 to 100,000 sensors. A refinery or a power plant, a chemical plant, 20 to 40,000 sensors. A large building, this isn't just, chemicals or anything else. A building, a large office building, 10 to 30,000 sensors. A transformer, 10 sensors. But the point being, all of these, this is integral to our entire society. Now I want to talk about a real case. This case was actually written up in the November 2022 issue of IEEE Computer Magazine, because this is showing that there actually, number one, there are problems, but there's a light at the end of the tunnel. If we do good engineering, we can maybe get ourselves out of a lot of the mess we're in to this day. This was a $1 billion manufacturing facility. They did this test not for cybersecurity, they did it for productivity. And they did it because all of their Windows displays, which everybody uses everywhere, said everything was fine. So they decided to do something different. They were going to look at using, quote unquote, modern technology. What they were going to do was look at the 4 to 20 milliamp currents. In other words, they were going to take the sensors and look at the physics of the sensors. And you can't hack physics. And then they were using machine learning, this whole world of AI, to be able to say, if we do this, do we see anything different than just looking at the signal that goes through all the conversion processes, becomes an Ethernet packet, and off on the Ethernet network, which has all kinds of opportunities for problems along the way. So they took one particular manufacturing line that had 16 sensors: pressure, temperature, flow, motor amperage, vibration, and valve position, which is representative of every single industrial or manufacturing facility everywhere, as well as a ship, you name it. Well, what they found was it was kind of mind-blowing. More than half of the sensors were either inoperable or out of calibration, and the Windows HMI didn't see any of them. The pumps, the big main feed pumps, were what was most critical to the operation of the facility, the productivity of it. The Windows HMI said everything was perfect. where everything was fine anyways. When they started monitoring the raw values, in other words, in real time, what they found was those pumps were experiencing problems, but they were occurring in seconds to less than a minute. Windows is too slow to see any of that. Windows was a consumer tool that was adapted, and industry has taken and run with it over the past 20 some odd years. This is all of what you're missing. Well, the net bottom line here is they did a detailed economic assessment of what it meant with the sensors and the pumps. This billion-dollar facility was taking a 3% hit on net productivity. This is a huge number. What you're looking at when you start talking about sensors aren't just cybersecurity, they're productivity, they're safety, they're everything. Like I say, they're your eyes, ears, nose, fingers. That's if you don't have that, you don't know what you're doing. What were the key project findings? This was not a cybersecurity project. Therefore, the engineers and plant personnel participated. If they would have called this a cyber project, the engineers wouldn't have been involved. This proves that if you do it right, you can get and overcome that that culture problem. The sensors are not near as accurate as we thought. I mean, I've did testing many years ago that said the same thing. Windows can be misleading, but we have all of this trust. And again, what's the Maginot Line for? Windows. There is significant information buried in the process sensors. We're just not looking. And finally, there's a real ROI. And what I call it is you're getting improved productivity, cyber and safety and everything else. And cybersecurity comes along for the ride. This is what the engineering world needs to do. Now, what does this also mean in the world of ransomware? You remember JBS meets, what happened with NotPetya, you name it. What happens is because we don't and aren't looking down at the engineering level, they don't know. So what would happen is when ransomware would hit, all of these companies would shut their facilities down, not because they had a problem, but because they didn't know whether they had a problem. An interesting one is with MKS Instruments. They had ransomware problem. They make equipment, really critical equipment, for all kinds of industries, including chip making. It turns out that, again, everything I'm telling you is public. Applied Materials, which is, I think, the largest, semiconductor manufacturing company in the world, took a $200 million hit on their quarterly report because MKS Instruments provides them with critical equipment used in the chip making. And here the ransomware didn't affect Applied Materials directly, but Applied Materials couldn't make equipment because their critical suppliers couldn't provide it. Now, going back to the previous slide about the monitoring of the sensors. By monitoring of the physics of the sensors, not just the sensors, it has to be the physics where any type of ransomware or malware simply can't get to. And what you're talking about there is that by monitoring the physics of the sensors, you have a justification to continue operating no matter what is happening with your networks, with your internet protocol networks. And the other thing that happened, I actually wrote a blog, and Marsh, the big insurance company, wrote something in there, and that's that a lot of companies are using business interruption insurance as a crutch, effectively, not to have to install control system cyber security technology. Well, if you start shutting down under an abundance of caution, not because anything has happened, but because you didn't know anything has happened, the insurance companies may no longer cover business interruption. This can be, tens of millions of dollars. So here's another reason why you should be doing that. Oops, I hit the wrong thing. Apologies. And the summary is this: any facility that measures or controls a process is at cyber risk. And it isn't just the Ethernet networks, serial point-to-point couplers, non-routable, are all, quote unquote, potentially immune to cyber. The damage can be existential. Today, and this goes, for your cybercrime center, you have no training or forensics to deal with equipment failures and distinguish those from cyber attacks. And finally, there's a light at the end of the tunnel, and it's not a train. And that is for control systems, not IT, but for control systems. If we treat them as engineering systems and use engineering approaches, we have a chance to be able to live through all of these cyber attacks that keep happening. The flip side is, if we don't and we continue down the path we're going, there is not a final upside at the end of that tunnel. So I think I took too much time, but with that, I want to open it up for questions. And if anybody, and by the way, I'm willing to stay longer if people have questions. So,
Joe, this is Jim Jones. Thank you very much. That was excellent. Very informative. We usually budget time past 1 o'clock for questions. So if you're okay with it, we'll go through a few questions and see what else pops up in the chat.
Yep.
Great. There was somewhat of a robust discussion in the chat while you were talking. You obviously triggered some thoughts, and in particular, Tom at INL and Jay at the Society of Automotive Engineers and I were going back and forth a little bit about kind of what's missing in the curriculum. And to your point that we train either engineers or cybersecurity people and not both, and there's very little crossover. So I'm curious, maybe, and Tom and Jay, I'm going to try to encapsulate that question that you all were talking about in one question here. So feel free to chime in. But what do you think is missing if you were to summarize it? We talked about, the hardware level things. You mentioned, I think, engineering forensics was the term that came up, and maybe mechanical engineering and the physics and control theory. But if you had the crystal ball and or the power and you were able to design a curriculum, what would you add to it, or how would you do it differently?
First of all, great questions, and thank you for asking. There is, first of all, the NICE work out of NIST doesn't address control systems at all. There is a community of practice that INL is kind of leading, I think, that is addressing the, if you will, the networking part of control systems. The piece that's missing is the actual devices themselves. I've actually given lectures and written stuff on this, whatever. Again, I'm a nuclear engineer. I started off having to deal with safety and instrumentation and all the rest of that. What's happening is, if you will, the things that can cause the safety or equipment damage part, the physics of the processes. This is not to make cyber people engineers, but what's important is to introduce the subjects at a level sufficient, really more for the network people to realize, oh my gosh, this is more than I know. I really do need to go next door and talk to the people who really do know this in detail. Okay. When I go back to, let me see if I can go back to this one chart or one slide. Wait a minute, let me see if I can go back. Anyways, without going back, if the Venn diagram, the purpose is not to make a Superman or a Superwoman who knows all about networks and control systems. The issue is to get each of them smart enough to know when to go to the others who are the experts. And that's not happened. I mean, like I say, when I give that presentation later this afternoon to the Secretary of Commerce's IoT Advisory Board, they're talking about education and everything else. None of it is going down to these types of devices. The minute they call it cyber, it's almost entirely aimed at networks. You know, and it's great to have HMIs. You see this all the time. You'll see HMIs, you'll see a PLC, and you'll have all of this other stuff. I mean, RSA is next week. You're going to see the ICS Village. It's going to have tons of HMIs and PLCs, and you're going to be lucky if you see one or two sensors. And they're not going to be looking at them. That's just feeding input. Jim, does that answer your question?
It does, and I see Tom's raised his hand. So Tom, feel free. Go ahead.
Hey, thanks, Jim. Great hosting on your part. And Joe, Tom Smirtnek, you and I know each other, and I'm an advocate for your experience and your knowledge, and you continuing to put out the word that the cyber physical systems, and as well as the physical cyber systems, are equally important, if not more important, because it's the next frontier in cybersecurity hacking by nation states, by people who maybe have gotten laid off in their tech jobs, and maybe they have an electronics engineering background and they want to do something new, but immediately financially beneficial. And so some people get drawn into the dark side, and we all know the various movies and TV shows that talk about that and highlight that. But what I did want to do is advocate for anybody who's in the audience who is looking to get their cybersecurity teams pulled together. Joe is a fabulous, I'll say, covalent type of person. He bonds very well with a lot of different people. He sometimes loses his voice because he does so much talking with his groups, but he needs to remember to keep some tea next to him when he does these pitches. But he's available. He will do projects for you, as he's described earlier in his presentation. He's gone out and been pulled in by companies, by various governmental agencies, and he's available. So reach out to him if you're with a corporation that needs some help getting going. There was a discussion here in the chat, Joe, that I'll end with. How familiar are you with the Society of Automotive Engineers, or Aviation Engineers, maybe now is what it is, the SAE, and their JA 7496 standard for cyber physical systems? What do you know about that? Can you add anything more?
Just a little bit. I've been a little bit in with G32, but I actually had a discussion and I'll bring this up because it's really, really, really fascinating. I think it was Tuesday or Wednesday, with one of the people from SAE from the aircraft side. Okay, he's an ex-pilot. And one of the things we were talking about was this whole issue of identifying a cyber incident. And I want to give you an example of what happened. I'm going to do this also, like I say, this afternoon. For those technical people, they'll know what I'm talking about. I'll explain more. There's a thing called a pitot tube, Pitot. And it's basically a tube for measuring airflow. And it's used in pipes, it's used in aircraft, it's even used in Formula One racing cars. And on an airplane, what it does is it converts that airflow into airspeed and altitude. Well, that particular sensor, or if you will, wrong readings from that particular sensor has resulted in more than 1,000 deaths from plane crashes. The same thing you have with, the recent, Boeing MAX 737s, were the angle of attack sensors, which is what essentially, flew those two 737s into the ground. The sensor issue is really, really, really important. And I also want to mention one other thing that Tom had mentioned. People call these cyber physical systems. They are not. These are physical systems with cyber connections. And this is also goes back to, Jim, kind of the question you asked. This has to be taught. A motor is not a cyber system. A motor is a physical system. A pitot tube, a sensor, is a physical system. The issue is they have cyber connectivity, whether that was meant to be or not meant to be. And that's what, if you will, the training needs to really go after. And a big part of this is actually also for the people, the engineers who are designing the equipment, because there are very little cyber requirements today down at the equipment layer. The cyber requirements are all at the communications layer. And that's part of why this training is so critical. Did that answer the question, or did I dance around it?
I think you hit right on it, Joe. Thank you. That was excellent. Tom?
Yeah, absolutely, Joe. You always do a stellar job, buddy. Appreciate
Thanks.
it. I enjoy hearing this every single time. Always something new that I hear.
Good. Thank you. Joe, someone else asked about some of the security that is in things like gaming systems. So I guess I'm assuming to protect the intellectual property, perhaps the gaming system will implement security on the bus within the unit. Do technologies like that have any place in control systems, or is that just a different animal?
No, it isn't a different animal. In fact, I mentioned that, we're working on a mathematical, or we did phase 1 and the proposal went in for phase 2, for using probabilistic mathematics to be able to determine where a hacker will go next when they're in, the network. Well, a goodly part of that is using game theory. So when you start looking at this, that's why, way back when I defined cybernetics, it really is a unbelievably wide cross-disciplinary subject. But game theory is really, really important, as you're going through any type of probabilistic approaches. And, the thing about cyber is there's an awful lot of probabilistic approaches buried in cyber.
Yeah, very good. Good, thank you. Joe, I recently saw a press release from a company that said essentially they can collect any telemetry from an industrial process, so analog and so on.
Right.
I'm curious, does that help at all? Is that only part of the solution? How would that capability fit into solving this?
It's part of, but not the solution, because part of it is what we're worried about is what is happening at the device itself, so that can we trust or do we know what's going on with the serial network or the the digital or IP networks. But our problem is the following, that the security world, particularly the OT security world, has made an assumption. The assumption is that the field devices, the sensors, actuators, etc., are uncompromised, authenticated, and correct. And what they do is they take that, if you will, serial signal, and it goes through, if you will, a serial to Ethernet converter. And by the way, that is what, the Russians bricked in the 2015 Ukrainian cyber attack. But the point being that we're worried about what is going on with that sensor itself. A friend of mine got his doctorate by hacking, it was either 3 or 4 different control system vendors. I think it was either a pressure or differential pressure transmitters. I mean, he hacked the transmitters. So if you're simply looking at the network, you're too late.
Yeah, good. Thanks, Joe. Tom, I see your hand up. I think you're still muted.
Yeah, I was trying to get to the mute thing.
Yeah.
Thank you, Jim. Joe, one of the more recent comments was by an educator who says that he has trouble describing and connecting the loss of safety to control systems. And it's something that you don't necessarily describe for lay people. And would you take a minute or two and describe, he says he's primarily a security researcher at a university, so he's not an educator.
Okay.
So he is one of the, I'll say, presumably a IT educated person who's gotten into security, but doesn't know the control system side. So he has a hard time connecting the loss of security in a control system at a particular level, right? Or that can't be done without some of the physical cyber knowledge, engineering, if you will. Can you describe how the loss of that security at layers 0 and 1 can affect safety?
Yeah, very much. I mean, and let me take it down to a really simple way. It's a person, okay? If you're colorblind and you come up to a flashing either yellow or a flashing red light, okay? I won't say a traffic light because you've got top, middle, and bottom, so you know where red, yellow, and green are. But if you have a single flashing light, and your vision is fine, you can tell the difference between it being yellow or red. But think about your colorblind. How would you tell the difference if it's a single light and if it's flashing yellow or it's flashing red? Now, that's a safety issue, okay? The point being, if a sensor sends the wrong signal, or if a sensor has been compromised and it's not able to get to its set point to be able to turn the safety equipment on, you have a major safety problem. You're going to, if you will, blow up a pipeline or have a train crash into another train, or you're going to have that airplane crash, or I can keep on going. The safety, and part of what the safety world does is use things like failure modes and effects analysis, or you have a number of different other types of detailed safety analyses, because what you're doing is you're assuming, you don't care why, you're assuming equipment fails for whatever reason. And you're saying, okay, if it fails, will my safety system still work, and will I still be safe? Well, one of the things cyber does, or two of the things it can do, is you're assuming that the operator is not going to do something stupid to exacerbate the problem. But with cyber, you can send misleading information to the operator to have the operator either take or not take the actions needed to keep things safe. The other thing that can happen is that you can have, you assume that all of the equipment will operate when and as it should. And with cyber, if you delay any of that, that's a very major safety issue. Does that help at all?
That'll be up to Eugene to decide whether he can take that and synthesize it for himself and let people know what he's learned today. And I believe he can. I believe he will. And thanks, Joe, for taking that minute to do that. I know you've got a congressional.
Yeah, that's it. I do have time if people still want to ask. It's a couple hours from now.
People, ask your questions. You don't have access to Joe every single day.
Eugene, you're up.
Thank you. Hi, Joe. I don't know you, but I wish I did. My name is Eugene Wasserman. I'm at Kansas State University. One thing with which I've had a lot of trouble, just to explain where I'm coming from with the safety thing, is I don't know a lot about electrical engineering. In fact, I'll say none. But when I've spoken with safety engineers and tried to explain the importance of security for safety, and we'll ignore for the moment whether it's low level, which you're identifying as layer 0 or below, but the conversation very typically goes, can your device do X? No. There was not enough time for the person to actually even think about whether the device can do it. I think they were responding directly from the requirements document.
Yes.
Then I say, let me rephrase that. Can your device be made to do X?
Mm-hmm.
And they go, no, in the same period of time. And then suddenly they go, oh, wait. Because I've identified a safety issue which can be made to happen if one were to manipulate their device a certain way, which is not expressly forbidden by the requirements.
Yes.
And suddenly, it's a safety issue. And I've been, for the last 7 years, more actually, I've been trying to get safety engineers to understand this concept. I've been trying to meet in the middle. It's very fun, but it's sometimes an uphill battle. And that is to what I'm referring. Security can clearly be a safety issue.
It is.
Frequently not obvious to folks that are trained in traditional safety engineering.
Well done, Eugene. Well done.
Yeah.
Well,
and by the way, what you just said was, this is going to come out wrong. Wonderful, because what you're saying is really the biggest problem we have in control system cyber is not technology, it's culture. It's the engineering side of the world and the security side of the world not wanting to understand each other. And like I say, that was one of the biggest problems that came out of that national cyber strategy. They exacerbated it by totally ignoring the engineering world. In fact, let me give you one other example. I gave a presentation, I don't know, about a month ago to CISA Region 10. Region 10 is Oregon, Washington, Idaho, Alaska. And one of the people from CISA used to be in a utility in charge of cyber. And so I asked this person, how many times did an electrical engineer attend a cybersecurity meeting, for NERC-CIP? Now, this is a utility. Who's the, being flippant, who's the most important people? The electrical engineers. The answer was once. And all of those meetings, once. And the engineer was there for 5 minutes and then left. Now, this is where we are. The system is completely broken. Eugene, like you said, in fact, this was me when I was at EPRI, at the Electric Power Research Institute, back in the mid to late 90s. The head of IT came into my office. I was running the fossil plant instrumentation controls program at the time. And he asked or begged me, would you please address cyber? And I told him, we don't care about email, get out of my office. And 20 or 30 years later, that's where people are. They view cyber as email. And the engineers are going, what effect does that have on me? And the flip side is, I had given a presentation here, I'm in the Bay Area, San Francisco Bay Area, to an InfraGard meeting, and a utility person was told to come see me. So over lunch, this person was responsible for the firewalls at the utility. And I asked them if there were a problem with the grid and they needed to, in a sense, shut the firewalls down so they could get the information necessary to keep lights on, what would you do? And you know what his answer was? I will not shut that firewall down. He would rather have had the lights go off than, quote unquote, shut the firewall. Now, he's working for an electric utility. What's his job? Neither the engineering world nor the networking world recognizes the importance of the other. And I say that as a general statement, there are people that don't. But until we solve that, and a lot of that, like I say, starts at the university level. When you do all of your training for cyber and completely ignore what that does to the physical world, you're asking for trouble. And when you do all, and in the domain engineering world, when you basically tell them, go and do anything you want that makes the physics better or the chemistry better, and you don't tell them, but oh, by the way, you got to be careful in how you do it, you're going to get where we are now.
Joe, thank you very much. Really appreciate your time and sharing your expertise and your experience with everyone. To the audience, really appreciate the engagement. Fantastic discussion. Joe's contact information on the screen there. Also, a video will be produced from this talk and posted to the CINA website. So CINA, CINA.gmu.edu. There's a digital archive. We'll include this talk and all of our past talks and other activities as well. And Tom, thank you. Tom dropped a note into the chat. There was a lot of good information in the chat during the talk. If you would like to save that chat before you disconnect, at the bottom of the chat box is a little three-dot ellipse. If you'll click on that, there's a save chat, and it will save it to your local hard drive. Has a little button there to open that folder because it's buried kind of deep. But Tom, thanks for that pointer.
Yeah, Jim, good job again. Great
Absolutely.
Can I
session.
mention one thing before we end? And
Of course.
Tom brought it up. For what it's worth, I am an independent consultant and I would like to help people if they're interested.
Excellent. Joe, thank you. If you can't find Joe somehow, please feel free to reach out to us at George Mason at CINA. I dropped the URL in the chat box there, CINA, CINA.gmu.edu. We're a DHS Center of Excellence. And thanks again, everybody. Really appreciate all the time and attention. Joe, thank you for your time. Good luck. We will certainly help you fight the good fight.
Jim, thank you for the invitation and thank everybody for their interest.
Good job, Joe. We'll see you
pleasure.
again. Talk to you soon.
Thanks, everyone.
So. Jim?
I'm still here, Joe.
Okay, I didn't, can you do me a great favor? Did you save the chats? Because I didn't.
Absolutely. I did. I will email that to you shortly.
Perfect. I hope this did what you wanted.
Very much, very much. And it's a sure sign that we hit a mark when the discussion runs another 30 minutes past the talk. And with that level of engagement from the folks, and in addition to Tom and some others chatting actively, had a bunch of, hey, thank you, this was great type of feedback. So really good. I really appreciate your time. I think you've hit on a gap that a number of us realized about 10 years ago in education, and we've been working to fix it. But I would say we're partway there and not as far as we need to be yet. So we're going to keep pushing in that direction.
Thanks for the invite.
Absolutely. Thanks, Joe. I will send you the chat in just a few minutes.
Sounds good. Take care.
Yep.
Bye.